So really we have to decide how to put arrows onto these. Which way are we going? Are we going in this direction or this direction? That's the only thing that you need to decide. And so how do we decide that? Well, when y is very small, so we write down here, then it means that x is growing. When y is very small, x is going to be growing. So when y is very small, x is going to be growing. And when x is very small, y is going to be declining. Is that right? When x is very small, this is negative. So that means over here we're going down, and over here, this doesn't. Where? Over here. Oh, sorry, x is small, so y is declining. Okay, right. And then so, then it'll go like this. So what happens is if you start off at a point here, you decline. You cross here vertically, you begin to grow. You cross here horizontally, you begin to grow. You cross here vertically, you begin to decline. You cross here horizontally, and then you decline down here, and then you cross here. And so you go around. Okay, so here, so you expect to wind around like that. Now, if you look at this, there's a lot of ambiguity. You don't know whether you're going to, the question is, are you going to wind out? Go like that. Are you going to wind out? Or are you going to wind in? Or are you going to make closed circles? So there's three options. And by just drawing this, you don't know which option you've got. So it's not clear from drawing something what the situation is. So in order to understand what the situation is, we actually have to look more closely at what's going on. Now, when we go through an analysis of this, well, I'll just show you what the answers are, and then we can move on, because the answer, in this case, so one of the ways of finding out is to build a ANOVA model and to simulate what's happening. So if you do the analysis, this is what you'll find out. And if you build an ANOVA model and you start out at different places, different initial conditions, you'll find that you actually make a closed loop. Now, this is an unusual behavior, and it's because this model is a very special case. In general, you'll see that when we change this model a little bit, this closed loop behavior will go away. Now, this closed loop in this particular case, the size of the loop depends on how far you are from the center when you start out. And one of the things you notice is that the loop is not a circle, and it's not an ellipse. And if you have to plot, remember, in the phase plane, you're plotting x against y. But as you move along, time is changing. So if I start out at a particular point, which I call t equals to 0, then I ask, where will I be at t equal to, say, 0.1? So this might be t equal to 0.1. Where will I be at 0.2? Where will I be at 0.3? Where will I be at 0.4? So what we say is that the line that we create is parameterized by time. Somewhere in there is time, and it's telling us how far we've gone. But we can just plot x and y against time. And as the solution goes round and completes a cycle, so the x trajectory will complete a cycle, and the y trajectory will complete a cycle. So when we plot x and y against t, we get the x and we get the y. When we remove t so that we have time implicit in this xy plot, then it's called a phase plane plot, and this is just called the solution trajectory. So don't get confused by those two things. This is the solution. Where you are on this curve depends where you start out. If I start out here and I call t equal to 0 here, then at t equal to 1 I will move a certain distance. If I start out over here at t equal to 0, then at t equal to 1 I'll be a certain distance. So it's not like time gives you a unique place on this curve. It depends where you start on the curve, but then after that, time will determine where you next are. So it's like, at some times, I can start out an initial condition that corresponds to x at this value, sorry, y at this value and x at this value. Or it may be y at this value and x at this value. So I can start at different values, which means I'm starting at different places on a particular curve. And on a particular curve, I get a particular solution. And the size of these oscillations will depend on where I start in the plane and which one of those curves I'm on. So each one of those curves is like a closed orbit, but the particular orbit I'm on depends on the initial condition. Now, it's not going to be like that for most models. It's only like this for a very special model. If you want to practice working with phase plane analysis in the textbook, you can look at example 2, which considers this differential equation. This differential equation is of no biological interest, so I'm not going to talk about it. It's just of interest on how to plot curves. But what we're going to do is we're going to have a look at this classification of equilibria in the phase plane. And as we go through different examples in the next couple of weeks, and we do a phase plane analysis, you'll see these different cases coming up. Now imagine I'm in the xy plane, and I've got a particular curve. I won't draw the whole curve because I'm just focusing on where they intersect. Now when I look, I know that if the red is the x dt equals 0, I know I'm going to cross it in either this direction or that direction, but I don't know which one, and it depends on the model. But what will happen is when you draw the arrows, there'll be different cases. So in one of the cases, the arrows will move in like that, and they'll all approach that point. That's called a stable node. Now if the arrows go in the opposite direction, so if you've got a point and the arrows go in the opposite direction, they will move out, then that's called an unstable node. If the arrows, so this is a node, this is unstable, and this is stable. If the arrows go around it, as we've seen, then if they wind out, then we've got a center, or a spiral. And this spiral is unstable. And sometimes they'll wind, you can start over here and it can wind in. And so this one is stable. So you get a stable spiral, an unstable spiral, a stable node, an unstable node. But then there's a fifth type, which is, when you look at this, you'll find that the arrows go like this. So it looks like you're approaching here in this direction, but you're actually going away in another direction. So this is what is called the saddle point. Now, the behavior of a system at a saddle point is called a saddle point because you can think of a saddle. If you think of a saddle is something that if you're going up to a mountain and you're going to a col. So, for example, imagine you've got a mountain peak over here and another mountain peak over here, and here's the low point. But you're going up and over. What happens is that when you're over here, you've got to walk uphill in that direction, you've got to walk uphill in that direction, but in this direction you walk downhill, and in the other direction you walk downhill. So that's like a saddle. A stable point like this is if you're in a bowl. So that no matter where you are in the bowl, you roll down to the center. An unstable point is like you're at the top of a hill. If you put a ball at the top of the hill, you can go down in any direction, and you'll go away from the top. Here, you can go down in any direction, and you'll go to the center of the bowl. Here, in some directions, if you put the ball over here, you'll start going towards this point. But depending if you start on one side or another, you might start going towards this point and roll down on this side, or you might start going towards this point and kind of roll down on the other side. Does everybody understand that? Okay, so those are kind of physical metaphors for these equilibria. And then, if it's closed like this, then we call it a center. So we can get the stable and unstable nodes, the stable and unstable spirals. The center is a very special case because it just happens that it closes on itself. And the saddle is an important case because it comes up very often. Now we're going to go to the development of the Lotka-Volterra model. So if we come back to the assumptions that we had over here, we can look at each of these assumptions in turn and we can modify them. So do prego grow exponentially? No. They may at low densities. Do predators decline exponentially? No, unless they're cannibalistic. Is mass action a reasonable portrayal of how much an individual takes out? So what it says is that if I'm an individual and I'm hungry, I go around and eat stuff. And as the amount of stuff increases, so I eat, the rate at which I eat is in proportion to that increasing amount. So for example, somebody says, okay, out there are 10,000 cookies, go find them. And every time I find a cookie, I eat it. And if there were 20,000 cookies, I would find them twice as often and I would eat twice as much. But if there were 100,000 cookies, I might be in the middle of eating one cookie and find another, and I'm not going to eat it straight away. Not only that, I'm going to start filling up. I'm going to slow down. So to assume that each unit of y, or each individual y, is going to consume x in proportion to its density is not reasonable. There's some kind of saturation. So when I look at an equation like this, I say there's many ways I can improve this equation. And in order to understand what the effects are, then I'm going to say, okay, I could change one term, see what happens. I could change another term, see what happens. And in doing that, I could say, okay, this assumption seems to be responsible for this part of the behavior. So one of the things that we see are oscillations. All these oscillations go away. What might cause the oscillations to dampen? So let's come back to this, and let's make a modification. And let's see what happens. So the modification that's easiest for us to make, because we kind of understand it best, because we've worked with a lot, is to assume that this is logistic growth rather than exponential. So what happens if we put in logistic growth? The x dt equals ax, 1 minus x, and let's see what notation I use. Okay. And then I still get this term vxy. And now I say, okay, dy dt equals minus cy plus dxy. Okay, so what do we think is going to happen? So in order to see what happens, now what we can do is we can do the phase plane analysis again, which I'm not going to do. I'm just going to show you what we get. And you can verify by working through the example that this is in fact what we get. So what happens is the null cline is x equal to 0 and y equal to a over b times 1 minus x over k. So when k was not there, which is the same as saying k goes to infinity. If k goes to infinity, then resources are not limiting. The carrying capacity is as large as we want. The previous case was k going to infinity. Now we've got a finite k. So instead of getting a straight line over here, we get a line with slope that is negative. And the slope is equal, the slope of x, the slope of this thing is affected by the value of k. So in fact, this line goes from AB, and instead of just going straight out, it now goes down because it has a root over here. Because when x equals k, y equals 0. So this line, instead of going over here, now turns down. If we take c over d, the y equations are still the same, the y null clines are still the same. So what we've really done is we've taken this x null cline from being horizontal and moved it down. And the larger k is, the less the slope is, and the larger k is, the more this tends towards the previous case. The slope gets less and less. Now what happens is you get the arrows going in the same way, but because of the angle over here, it has to turn down more quickly to be able to go through the vertical. And in fact, what happens is the oscillations dampen, and this turns out to be a stable equilibrium. So this is a stable spiral now. So we're spiraling around, but it's a very tight one. And although actually it's still oscillating here, it's like oscillating in the 6th or 7th decimal place, and then the 8th decimal, and then the 9th. So you can't see these oscillations anymore because they're too small. So it looks like it's a straight line. And if you go for time long enough, it will be a straight line in terms of approximating to 4 decimal places or 5 decimal places. But somewhere off in like the 20th decimal place, it may still be oscillating, and then the 30th decimal place. So mathematics has this quality of the solution has to be asymptotic. It never gets there, but it gets closer and closer and closer as time gets larger and larger and larger. But for all practical purposes, you can't see this anymore. Okay, so you understand what happens. So you can say that without having the carrying capacity in there, the predator population can limit the prey population. It limits it. It stops it growing exponentially, and it brings it down. But it can't stabilize it. It brings it down. It overshoots too much. Then it goes up again. So it gets into an oscillation. So if we look at the lynx hair data, you can say there's an oscillation, and it would be stabilizing, but it doesn't stabilize very rapidly, which means for the hair there's probably a large K compared to where the prey would control it down to. But because of small environmental perturbations, it's these environmental perturbations that keep knocking the population one way or the other, so it keeps it oscillating. So for example, in biology, you can never expect out there that a population would be in equilibrium. Because to be in equilibrium, we're assuming a constant background. We're assuming a constant background because we're saying the environmental carrying capacity is fixed, these parameters are fixed. But the environmental carrying capacity for rabbits may be linked to precipitation. And in wet years, there may be more grass growing than in dry years. So this point moves around. And every time it moves around, the population then circles around it and makes another loop. So it's like the population is trying to change an equilibrium that's changing. But the equilibrium is oscillating back and forth in this region, and the population is chasing it around and around. So the sustaining oscillations you get there are due to the fact that there's environmental effects that make the assumption about your parameters being constant not a reasonable assumption. Okay, so let's go to the next thing we can do. The next thing we can do over here is to say that we assume that the mass action assumption is not a good assumption because it's some kind of satiation. So let's talk about satiation. So I'm going to put in a satiation function, phi of x. Okay, and we'll see what we think satiation functions might look like. Sorry, that's the wrong one. You have to be pretty smart to do this properly. Obviously, I can't multitask. So we're coming over here and we're saying, I'm going to take this term bx. And over here, if you remember, I said we've got something called kappa bx. And I call that d. I'm going to revert back to bx because what I want to do is I want to take bx and I want to call it phi of x. And so here's x, and here's the function. And if I say this function phi of x is just b times x, I've got a line like that. Now, if we talk about satiation, you can say, what does the satiation curve look like? Well, it might be that under normal circumstances, I eat 2 cookies an hour for the rest of my life. That's what I need. I don't do anything else. So there are cookies out there, they've been hidden in the woods, and I go look for them. And I get 1.5 cookies an hour. So I say, okay, I just keep eating whatever I can. And if I go up, if the density of cookies increase and I can find them at 1.7 cookies an hour, then I eat 1.7 cookies an hour. So I eat as many cookies as I can up to a maximum of 2. And then when I can collect more than 2 cookies an hour, I just stop and I only eat 2 cookies an hour. So as the density of cookies go up, I try to get what I can get until I satiate. So that's called a type 1 response function. That's type 1. And we call it a Holling type 1 because in the late 1950s, a very famous ecologist by the name of Buzz Holling went out into the woods, and what he did is he looked at these little rodents that collect sawfly larvae. Sawfly are like a primitive kind of bee, and they make cocoons, and they fall into the leaf litter, and the little rodents go and find them. And then he said, how many would they gather as the density of sawfly larvae go up? But one of the things that you can analyze is the fact that there's a handling time. So for example, it's not just like, if I see a cookie, I eat it. It takes me an instant from the time I see the cookie to the time I eat it. It takes me time to bite into the cookie, chew it. If it's a nut, it takes me time to open it up and get the nut out. And so there's something called a handling time. So of all the time that I've got some time for searching for things, and when I find them, I've got a fixed time after I found it for handling it. And so as I find more and more of my time is devoted to handling and less to searching. And so what the effect of that is that instead of having a corner like this, I start coming